The night of the 24th of July, 1943. A lone Lancaster bomber crosses the North Sea at 18,000 feet, its 4 Merlin engines thrumming steadily through air thick with coastal haze. Inside the fuselage, the wireless operator reaches for a canvas sack, one of dozens stacked along the bomber's walls. At precisely 2,247 hours on the navigator's signal, he tears open the sack and upends its contents down the flare chute. Thousands of thin aluminium strips, each exactly 27 centimeters long and 2 centimeters wide, tumble into the slipstream. They catch the moonlight for a moment, a brief metallic shimmer, before dispersing into the darkness behind the aircraft. The crew member reaches for another sack, then another. By the time the bomber crosses the German coast, it has released nearly 2 million strips of metal-coated paper, each one fluttering earthward at approximately 3 meters per second, each one sending back a radar echo indistinguishable from that of a bomber itself. On the ground at Stade, north of Hamburg, a Luftwaffe radar operator stares at his Würzburg scope in mounting confusion. Where moments before he had tracked a single contact, his screen now blooms with dozens of returns, then hundreds, then so many overlapping echoes that the entire display dissolves into a churning mass of light. He calls urgently for his supervisor. Within minutes, every German radar station along the coast reports the same phenomenon. Controllers attempt to vector night fighters toward the bomber stream, but the instructions become meaningless. The night fighters climb into skies that their ground controllers can no longer map. The carefully constructed system of ground-controlled interception, refined over 3 years of night warfare, renders itself useless in the span of 12 minutes. Nobody at Stade knew they were witnessing the operational debut of Window, though the phenomenon would soon acquire its German designation, Düppel. Nobody knew that this simple countermeasure, requiring neither electronics nor complex engineering, would alter the calculus of the night bombing campaign more thoroughly than any technological advancement since radar itself. The aluminium strips fluttering down through the darkness over northern Germany represented the culmination of 3 years of debate, fear, and postponed decisions within the highest echelons of British command. The problem Window addressed was brutally simple and mathematically devastating. By mid-1943, Bomber Command's losses over Germany had reached unsustainable levels. During operations in the spring of 1943, loss rates frequently exceeded 5% per mission. The mathematics were unforgiving. At such rates, a bomber crew's statistical life expectancy stood at fewer than 14 missions. Since operational tours comprised 30 missions, the probability of surviving a complete tour fell below 30%. These were not the casualties of a bad night or an unlucky raid. They were the steady, predictable attrition of a defensive system that worked with mechanical efficiency. The German night fighter force, orchestrated through the Kammhuber line, an integrated network of radar stations, searchlight belts, and fighter zones stretching from Denmark to Switzerland, destroyed British bombers with industrial regularity. Each Himmelbett, or 4-poster bed zone, contained a Freya early warning radar and 2 Würzburg precision tracking radars. One Würzburg followed the bomber, the other tracked the fighter. A controller in a central operations room guided the fighter on to an interception course, reading out ranges and bearings with methodical precision. The system worked. During the first 4 months of 1943, Bomber Command lost 872 aircraft to night fighters, with another 2,126 damaged. The Reich's defenses were destroying bombers faster than British factories could build replacements. The solution had been understood since 1937. Scientists at the Radio Research Station at Slough had discovered that metal strips, cut to half the wavelength of a radar transmission, would reflect radio waves with extraordinary efficiency. A strip of aluminium measuring 27 centimeters would return an echo on the German Würzburg radar, which operated at a wavelength of 53 centimeters, comparable to that of a bomber's fuselage. The physics were elegant, the application devastatingly simple. Release millions of these strips over Germany, and every radar scope would become saturated with false targets. The carefully managed ballet of ground-controlled interception would collapse into chaos. Yet window remained unused. For 3 years, vast quantities of the strips were manufactured, stored in warehouses, and kept from operational deployment by a single paralyzing fear. If Bomber Command used window, Germany would immediately understand the principle and could deploy identical countermeasures against British radar. Britain's own defensive radar network, which had proven decisive during the Battle of Britain, would become equally vulnerable. The chain of coastal radar stations that had given crucial warning of incoming German raids could be rendered blind. Fighter Command's ground-controlled interception, the very system Britain had pioneered, would face the same saturation and confusion. The stalemate persisted through 1941 and 1942. Window production continued. Approximately 2,000 tons were manufactured and stockpiled, enough to equip the entire bomber force for months of operations. Scientists refined the design, experimenting with different materials and configurations. The standard window strip consisted of black paper, 220 millimeters long, with thin aluminium foil bonded to both sides. The total width, including the paper substrate, measured 2 centimeters. Each strip weighed less than half a gram. A single bomber would carry approximately 2,000 bundles, each bundle containing roughly 2,000 individual strips, packaged in brown paper wrapping that dissolved quickly when exposed to the slipstream. The designer of the operational window system was Joan Curran, a physicist working with the Telecommunications Research Establishment. She had studied the radar reflection characteristics of various materials and configurations, ultimately determining the optimal dimensions for maximum effect against German radar frequencies. Her work extended beyond mere calculation. She designed the dispensing mechanisms, established the release rates that would maintain continuous radar coverage, and calculated the descent characteristics that would keep the strips airborne long enough to sustain the deception. A bundle of window, when released at operational altitude, would take approximately 20 minutes to reach the ground, slowly expanding into a cloud several hundred meters across. Properly deployed, a bomber stream could create a continuous corridor of false echoes extending for hundreds of kilometers. Manufacturing window required no exotic materials or complex processes. Rolls of aluminium foil, identical to household cooking foil, were cut into strips and bonded to paper. The work was carried out by civilian workers, many of them women, in converted warehouses. By early 1943, production had reached sufficient capacity to supply every bomber in the command. The cost was negligible, approximately £1 per million strips. For comparison, a single Lancaster bomber cost £45,000. The most economically efficient defensive countermeasure in the entire war could be manufactured for less than the price of a single machine gun. The decision to finally deploy window came in June 1943, driven by the brutal arithmetic of loss rates and the deteriorating prospects for the bomber offensive. Lord Cherwell, Churchill's scientific advisor, presented the case with characteristic bluntness. Without window, the bombing campaign would exhaust itself through attrition before achieving strategic effect. With window, losses could be cut by at least 2/3. The risk to British defences, whilst real, had become acceptable. Germany's bombing campaign against Britain had diminished to occasional nuisance raids. The Luftwaffe lacked the heavy bomber force necessary to exploit window, even if they understood its application. Furthermore, Britain's defences had evolved beyond pure radar dependence. Ground-controlled interception remained important, but fighter pilots increasingly relied on airborne interception radar, visual acquisition, and tactical flexibility. On the 15th of July, 1943, Air Chief Marshal Sir Arthur Harris received authorization to deploy window operationally. The target selected for its debut was Hamburg, Germany's second-largest city, a port complex of immense strategic importance and a target that required a deep penetration over heavily defended territory. The operation, designated Gomorrah, would test window under the most demanding conditions imaginable. The first wave of bombers departed British airfields on the evening of the 24th of July. Each aircraft carried its standard bomb load, plus approximately 2 tons of window bundles. Crews had been briefed on the new countermeasure only hours before takeoff, with strict instructions that the information constituted an absolute secret. The dispensing procedure was simple, almost to the point of tedium. Beginning at the enemy coast, one crew member would release bundles down the flare chute at precisely 1-minute intervals. The bundles would break apart in the slipstream, releasing their contents across several hundred cubic meters of airspace. The task typically fell to the bomber's wireless operator or gunner, whoever could be spared from primary duties during the critical approach phase. The work proved physically demanding and monotonous in equal measure. Bundles weighed approximately 1 kilogram each. A full load meant handling nearly 2,000 kilograms of packages during a flight that might last 7 or 8 hours. The bundles had to be opened and dropped individually, one every minute, maintaining rhythm despite flak bursts, fighter attacks, or the violent maneuvers a pilot might execute to evade threats. Crews quickly developed routines. Some wireless operators stacked bundles within arm's reach before crossing the coast, creating assembly lines that minimized movement. Others worked in teams, one crew member opening bundles whilst another handled the actual release. The physical evidence of Window's effectiveness became apparent before radio confirmation from ground stations. Crews observed searchlight batteries behaving erratically, beams sweeping across the sky in confusion rather than locking onto individual aircraft. Predicted flak, which relied on radar-directed calculation of bomber altitude and course, became noticeably less accurate. Barrage flak intensified, as German gunners compensated for reduced accuracy with increased volume, but even heavy flak proved less lethal than the precisely calculated fire that radar direction enabled. Most tellingly, fighter attacks diminished dramatically. Bombers that would normally expect multiple interception attempts during a deep penetration raid reported encountering no fighters at all, or seeing night fighters orbiting aimlessly in the distance, their ground controllers unable to provide coherent vectoring. The effect exceeded even optimistic predictions. German radar operators reported their scopes obliterated by false returns. Würzburg radars, which could normally distinguish individual bombers at ranges exceeding 80 kilometers, became effectively blind beyond 30 kilometers. Freya early warning radars, operating on longer wavelengths and therefore less susceptible to Window's specific dimensions, still showed such dense clutter that estimating bomber numbers or tracking individual formations became impossible. Ground controllers attempted to direct night fighters toward concentrations of echoes, but the instructions devolved into guesswork. Night fighters climbed toward reported altitudes only to find empty sky or found themselves amid the bomber stream but unable to receive coherent vectoring toward specific targets. The 791 bombers attacking Hamburg that night lost 12 aircraft, a loss rate of 1.5%, less than a third of the recent average. The bombing itself achieved unprecedented concentration. With night fighters disrupted and searchlight batteries unable to track targets effectively, bombers flew straighter, steadier runs over the aiming point. The resulting fires overwhelmed Hamburg's civil defenses, creating conditions that would, over 4 subsequent raids, generate the first firestorm in military history. The German response combined immediate tactical adaptation with longer-term technical countermeasures. Within 48 hours of the first window raid, Luftwaffe Fighter Command issued new operational procedures. Night fighters were ordered to patrol free hunt zones over target areas, rather than rely on ground-controlled interception. Pilots were instructed to climb to altitude and search visually for the glow of bomber exhausts against the cloud cover. The Himmelbett system, with its careful zoning and controlled interceptions, gave way to a more chaotic but more flexible approach known as zahme Sau, or tame boar. Single-engine day fighters were added to the night battle, ordered to climb above the bomber stream and dive onto targets silhouetted against the fires below. Technical responses followed within weeks. German radar operators discovered that by reducing receiver gain and accepting shorter detection ranges, they could partially see through window clutter. Modified Würzburg sets, equipped with narrower bandwidths and improved discrimination circuits, could distinguish moving targets from the slowly descending strips. The modification required careful calibration. Set the gain too low, and genuine bomber returns disappeared along with the chaff. Set it too high, and the scope remained saturated. Operators learned to adjust sensitivity dynamically, reducing gain when window density peaked, then increasing it to catch bombers emerging from the chaff corridor. The Luftwaffe accelerated development of airborne interception radars that operated on centimetric wavelengths, frequencies for which window strips would need to be impractically small to produce effective echoes. The SN2 radar, operating at 90 centimeters wavelength, entered service in autumn 1943 specifically to counter window saturation. The new radar proved moderately successful, though it carried penalties. The longer wavelength reduced resolution, making precise range determination more difficult. The antenna arrays required for SN2 were bulkier and heavier than previous designs, degrading night fighter performance. Mounting the aerials on a Bf-110's nose increased drag by approximately 8%, reducing maximum speed and climb rate at precisely the moment when German fighters needed every advantage against increasingly well-armed bombers. Other countermeasures emerged through operational necessity rather than engineering laboratories. Experienced night fighter pilots discovered they could use window itself as a tracking aid. The chaff corridors marked the bomber stream's path as clearly as a motorway through the countryside. Rather than attempt interceptions from ground control, fighters would patrol alongside the visible window trail, waiting for visual acquisition of individual bombers. This tactic, known as wild sow or wild boar, transformed night fighting from a controlled technical procedure into a form of aerial hunting that relied heavily on pilot skill and aggressiveness. The introduction of single-engine fighters to the night battle represented another adaptation forced by window's effectiveness. FW-190s and Bf-109s, aircraft designed for daylight combat, were pressed into service as night fighters. Stripped of unnecessary equipment and fitted with minimal radio gear, these fighters would climb above the bomber stream and attack by diving from altitude. The approach worked best when fires on the ground silhouetted the bombers against the flames below. On clear nights or against targets that failed to generate significant fires, the single-engine fighters proved far less effective, often unable to locate any targets despite flying through skies that ground radar showed as thick with bombers. Britain's deployment of window had not occurred in isolation. The United States, conducting daylight bombing operations over Europe, observed the results with intense interest. American scientists had independently developed their own radar countermeasure, designated Chaff, using similar principles but slightly different dimensions optimized for American radar frequencies. The Americans faced a different tactical problem. Their bombers operated in daylight, in tight formations, relying on massed defensive firepower rather than darkness and dispersion for protection. Chaff proved less tactically decisive for daylight operations than window had for night bombing, but American bombers began carrying it nonetheless, adding to the general radar confusion over German airspace. Germany, predictably, developed its own countermeasure within months. Duple, manufactured to British specifications after examination of recovered window samples, entered production in late 1943. Yet German use remained limited and sporadic. The Luftwaffe's bombing capability against Britain had withered to the point where radar countermeasures offered marginal advantage. When Germany did employ Duple during the retaliatory baby blitz raids of early 1944, it achieved local success in saturating British radar coverage, but the small scale of the raids prevented strategic impact. The mathematics of window's effectiveness evolved as both sides adapted. Initial loss rate reductions of 70% eroded within 3 months as German defenses adjusted. By winter 1943, loss rates had climbed back above 4% on heavily defended targets. Yet window remained tactically essential. Without it, loss rates would have reached 7 or 8%, levels that would have made operations suicidal. The countermeasure had bought time, reduced casualties, and forced the Luftwaffe to disperse resources into countermeasure development rather than expanding fighter production. The broader strategic impact proved more complex than simple casualty statistics suggested. Windows deployment marked a turning point in electronic warfare, demonstrating that relatively simple, low-technology countermeasures could temporarily neutralize sophisticated defensive systems. The psychological effect on German radar operators and night fighter crews proved significant. Confidence in ground control, previously absolute, eroded into uncertainty. Night fighter pilots, forced to rely more heavily on visual acquisition and individual initiative, faced increased stress and fatigue. The disruption rippled through the entire defensive network, complicating coordination, increasing response times, and degrading overall system efficiency. Post-war analysis revealed additional dimensions. British intelligence had significantly overestimated the immediate German capacity to deploy Dupel against Britain in retaliation. The decision to withhold window for 3 years, whilst understandable given the information available to commanders at the time, had cost thousands of aircrew lives unnecessarily. The countermeasure could likely have been deployed as early as 1941 without catastrophic consequences to British defences. The 3-year delay represented a failure of risk assessment, a tendency toward worst-case analysis that paralysed decision-making in the face of uncertainty. Window's legacy extended far beyond the Second World War. The principle of radar jamming through metallic chaff became standard procedure for military aircraft worldwide. Modern chaff differs only in details from the original window design. Strips are cut from glass fiber coated with aluminium rather than paper and foil, providing better durability and more consistent radar returns. Dispensing systems have become automated, releasing chaff bundles in response to radar warning receivers. But the physics remain identical. A properly dimensioned metal strip, released in sufficient quantity, will overwhelm a radar receiver through sheer volume of false returns. The mathematical elegance of Window's design persists. The optimal strip length remains half the wavelength of the target radar, a relationship that flows directly from the physics of electromagnetic reflection. Modern military radars operate across a broad spectrum of frequencies, requiring aircraft to carry multiple types of chaff, each cut to specific dimensions. A fighter aircraft's chaff dispenser might contain bundles optimized for search radars operating at 1-meter wavelengths, fire control radars at 10 centimeters, and missile guidance radars at 3 centimeters. The principle Joan Curran worked out in 1937 governs the defense of aircraft 7 decades later. Surviving examples of original window strips exist in museums across Britain, typically displayed alongside other radar equipment from the period. The Imperial War Museum maintains samples in climate-controlled storage. The RAF Museum at Hendon includes window in its Bomber Command exhibition, though the fragile nature of the paper and foil construction means few original samples remain in displayable condition. More commonly, museums display reproductions or later versions manufactured for post-war testing. Occasional discoveries still occur. Construction work in Hamburg occasionally unearths concentrations of window strips, preserved in anaerobic conditions beneath building foundations. The aluminium has typically corroded, but the distinctive dimensions and the sheer quantity of identical strips make identification certain. Archaeological excavations at former Luftwaffe airfield sites sometimes recover German Dupel samples, providing physical evidence of countermeasure deployment that paper records do not always capture. The story of window remains instructive precisely because of its simplicity. The most effective countermeasure of the electronic war required no sophisticated manufacturing, no rare materials, no complex assembly. It demanded only understanding of fundamental physics and the courage to deploy it despite legitimate fears of retaliation. In this, it embodied a recurring pattern in military technology. Complexity generates new vulnerabilities. Sophisticated systems create dependencies that simple countermeasures can exploit. The defensive network that protected Germany, built on cutting-edge radar technology and carefully orchestrated procedures, proved vulnerable to strips of household aluminium foil tumbling through the darkness. The Germans had built an elegant machine for destroying bombers. The British defeated it with confetti.